This video presents the design, development, and testing of Spirit 9 for AUVSI's 2017 SUAS competition. Spirit 9 is an octocopter featuring efficient propulsion, autonomous guidance, and large payload capacity. Spirit 9 was designed to include a custom-designed sense, detect, and avoid algorithm and 3D printed parts. All aspects of the UAV will contribute to improved performance during the mission demonstration. My name is Vail Tolpagan. I am a junior. I will attend Flint Hill High School next year. I have been on Team Animus Ferus for 3 years in total, 2 as a team programmer and 1 as team leader. I have several years of experience with UAS technologies, and I will be leading the team at the mission demonstration.
My name is Manav Gandhi, and I'm a high school senior. I'm planning to attend Virginia Tech in the fall. This is my first year on Animus Ferus and my first year working with UASs. I am part of the mechanical sub-team, and I'm going to be the safety pilot on the flight line.
My name is Dylan Tresky. I'm a junior at Flint Hill School, and I'm the backup safety pilot for the team. This is my first year on the team, but I've had a few years of experience with small multi-rotors and fixed wings. My role on the flight line is antenna tracking and monitoring radio frequencies.
My name is David Pillay. I am a current senior, and I will be attending George Mason University in the fall. I am the safety officer, which is my role on the flight line. I have 1 year experience, and this is my first year with UASs.
My name is Jack Harrington. I'm a high school senior, and I will be attending the University of Virginia. I'm a new member of Animus Ferus, and this is my first year working with UASs. I am part of the programming sub-team and will be operating the ground control station at the flight line.
My name is Aiden Fitzgerald, and I'm a senior at Flint Hill School and will be attending Christopher Newport University in the fall. This is my first year on Animus Ferus and working with UASs. I am on the mechanical sub-team and will help set up the UAV on the flight line.
My name is Robert Fitzgerald. I am a high school senior and will be attending Virginia Tech next year. This is my first year on Animus Ferus, and this is also my first year working with UASs. I will be part of the mechanical sub-team, and on the flight line, I will be in charge of setting up the imaging system.
My name is Gianna Fiore, and I'm a senior at Flint Hill. I plan to attend George Washington University in the fall. This is my second year on the team, and I currently work on documentation. On the flight line, I will be communicating our progress to everyone off of the flight line.
My name is Peter Cusician. I am a high school senior and will attend Cornell University next year. I have been on the team for 1 year as a member of the programming sub-team. I will be managing image processing on the flight line and have 1 year of experience with UASs.
My name is James, and I'm a junior at Flint Hill School. This is my first year on Animus Ferus and working with unmanned aerial systems. I am part of the programming sub-team. My job on the flight line will be to operate the SDA viewer.
Spirit 9 was designed to complete all mission elements. During the mission demonstration, Spirit 9 will accomplish 100% autonomous flight, a successful airdrop, and interoperability submission of location data as well as target submission data. All other tasks are new to the system and will be attempted but are not guaranteed to succeed. Emergent target tasks will not be attempted. Further information about each competition element is provided later in this flight readiness review.
After a thorough analysis of the previous flight system, Team Animus Ferus identified the propulsion system as a significant loss of efficiency. Improving the performance of the propulsion system was a top priority to maximize flight time. Since Spirit 9's motors were carefully selected for their high efficiency and performance, the loss of efficiency was determined to be caused by the propellers. Many propellers made of different sizes, pitches, and materials were bench tested, ranging from 15-inch diameter propellers used last year to 18-inch diameter propellers. Additionally, thrust calculations were completed to determine the maximum theoretical static thrust of each propeller. 18-inch 6.5 pitch carbon fiber propellers and 16-inch 6-pitch carbon fiber propellers were chosen as potential propellers for Spirit 9. Unfortunately, the 18-inch 6.5 pitch carbon fiber propellers would overlap with neighboring propellers, potentially causing unstable flight. The team chose to use the 16-inch 6-pitch carbon fiber propellers. The thrust-to-weight ratio of the 16-inch 6-pitch carbon fiber propellers on Spirit 9 is 2.55 to 1, ensuring the UAV is very responsive during flight. Theoretical thrust calculations were completed, and throttle tests on the competition platform were conducted. By using 3 separate metrics to independently verify the thrust and current draw, the team was able to ensure that the system would perform as expected during all competition tasks.
For the 2017 SUAS competition, the team decided to build upon the airframe used during last year's competition. Constructed out of carbon fiber, the previous base frame consisted of 8 arms, 3 center plates, and landing gear arranged in a triangular format. Improvement made to the airframe allowed for a 1.6 pound reduction in frame weight. Additionally, cross-sectional area along the z-axis was minimized, reducing drag in flight. In order to accommodate a second GPS module and decrease PIXLOC vibrations, a fourth carbon fiber plate was added, which serves as the hub for the PIXLOC and all accompanying sensors. Additionally, the plate provides the battery's safety in event of an unstable takeoff or landing. Another improvement to the airframe included the removal of the rail system. This removal opened up space on the underside of the craft, allowing for an airdrop and camo gimbal to be mounted alongside each other. As a result, mission time is much lower since all tasks can be completed during a singular flight.
After researching many of the available cameras, the team came down to two choices, a Point Grey Fleet 3 and a Samsung NX500. After reviewing the images from both cameras at an altitude of 370 feet, the team found that the Samsung NX500 images were of superior quality. In addition to the camera, a 3-axis gimbal was used to minimize camera vibration during flight. Using pixels per square inch calculations, the team was able to determine Spirit 9's maximum flying altitude during these search area tasks. Through testing, the team found that the flying altitude, 550 feet, objects were detected at a rate of 80%. This altitude also minimized the mission time required to complete this task. In order to determine the effect of motion blur on the targets, images were taken at various velocities ranging from 0 to 15 knots. The results provided by these tests showed that velocities exceeding 15 knots resulted in motion blur that affected ODCL accuracy. As such, the team decided that Spirit 9 should fly through the search area at 15 knots to minimize flight time while maximizing accuracy.
For the task of testing and training target classification components, a synthetic dataset generator was created for its ability to cover the multiple classification permutations possible and for its relative convenience in amassing large sets of targets. The generator is capable of creating both full-sized images that contain any number of targets overlaid onto images taken at previous competitions, or crops of single targets over previous competition images. Along with these images, a target file is created for each containing the specifications of each target present in the image, so the performance of the image processing system can be easily evaluated by computer. The accuracy of the target detector was assessed using a set of 370 full-size generated images, each containing 10 targets. A target is scored as being correctly identified and cropped if the center of the target's crop is within 50 feet of the correct target position by using the pixels per square inch of our camera at the height the generated image emulates. Of 3,700 total possible targets, 2,750 were correctly identified and cropped, with a total of 173 false positives. The accuracy of our classification algorithms was assessed using a set of 10,000 individual target crops, yielding an accuracy of 77% for orientation, 82% for shape, 96% for target color, 65% for alphanumeric classification, 85% for letter color, and an overall accuracy of 81%. Using the performance of the localization and classification algorithms, our predicted score for object detection, localization, and classification is 72.27% of the total possible points.
After extensive testing of multiple iterations of airdrop mechanisms, the team concluded that the most practical solution included a servo control clasp on a horizontally mounted barrel. When the servo is in the closed position, it locks the two sides together and encloses the water bottle within. Once above the drop location at an altitude of 110 feet, the servo rotates out of the way, allowing the water bottle to escape the mechanism. To increase vertical drag and visibility, the parachute is attached to the water bottle. The water bottle is also enclosed in a wrapping of bubble wrap and duct tape, allowing the impact force to be absorbed over a longer period of time. Within the use of a new airdrop mechanism, the team is able to accomplish pinpoint accuracy during drops. Drop precision was aided by the craft's ability to maintain a single position throughout the drop. Numerous tests showed accurate and precise drops throughout winds exceeding 10 knots. After performing a statistical analysis of the 18 drops performed by the craft, the team found that on average the airdrop landed 24 feet away from the target location. All drops resulted in no damage to the water bottles and its contents.
Spirit 9 is powered by two 6S 16,000 mAh LiPo batteries connected in parallel. The maximum amp draw available from these batteries is 320 amps continuous discharge. At full throttle, Spirit 9 systems draw just over 165 amps. However, during takeoff, Spirit 9 was observed to draw an average of 56.6 amps. At rest, the system does not draw more than 3 amps.
Animus Ferus uses a Pixhawk PX4 running Arducopter as Spirit 9's autopilot. In order to communicate with the autopilot, the team's ground control station runs Mission Planner on one computer and MAV proxy on another. Mission Planner offers a user-friendly interface that allows the team to plan, supervise, and control missions, while MAV proxy serves as a direct link to the UAV that allows for duplication of the communication pipeline, allowing scripts to function in conjunction with Mission Planner. During the team's testing, guidelines were established to ensure that the team's safety if communication between the autopilot and the ground station is lost, or if the UAV breaches its geofence. Each scenario, including the breaching the geofence, was tested to ensure the craft responded appropriately. During tests, every system component operated correctly.
The autopilot system for Spirit 9 is the Pixhawk platform using the Arducopter autopilot. Dual GPS modules and compasses are implemented for redundancy. At any point in time during the mission demonstration, if there is a failure of the autopilot, the safety pilot will be able to take over and guide the UAV to a safe landing location. Extensive testing was conducted to ensure the autopilot would be able to successfully pilot the craft in all expected weather conditions. Over 5 hours of autonomous flight time in competition configuration were completed with Spirit 9 with no crashes during flight. In addition, controlled failures of the communication links were conducted to ensure the UAV responded correctly if it lost communication with the ground station during the mission demonstration.
To visualize all competition elements in one single application, custom visualization software was created. Using a combination of HTML, JavaScript, PHP, and a MySQL database, the visualizer displays the UAV's position and the current mission information. The visualizer refreshes multiple times per second, ensuring live data is always displayed. This is the software that the judges will use to view the status of the UAV and all competition elements. During full mission tests, the viewer was tested to ensure that all functions work. In addition, using an Arducopter SITL, or Software in the Loop instance, the team was able to test the viewer in a sandbox environment to minimize potential damage to other systems.
Using a custom set of algorithms implemented in Python, the UAV is able to complete the sense, detect, and avoid mission task. The script identifies obstacles out of data that is pulled from the interoperability server and determines a new position for the UAV to move to, and completes the action through a connection to MAV proxy. Numerous different methods of testing were completed. First, all algorithms and integration scripts were tested using over 25 unit tests. Next, algorithms were thoroughly tested in simulated environments, avoiding obstacles. 4 stationary obstacles and 1 moving obstacle were tested in simulation. All obstacles were successfully avoided in the simulation testing. Due to time constraints as well as development issues, the team was not able to test the sense, detect, and avoid algorithms on Spirit 9 at the time of filming. At competition, the team expects to avoid all stationary obstacles and some of the moving obstacles. After completing several mission tests, Spirit 9 averaged 45.6% of possible mission demonstration points. During the first mission test attempted, the team scored 41.6%. On the second and third full mission tests, the team scored 46.8% and 48.4% respectively. Due to time constraints, the team was not able to test ODCL and SCA during these mission tests. During all mission tests, Spirit 9 captured all waypoints, did not go out of flight bounds, and successfully completed the airdrop mission task. At competition, the team expects the mission demonstration score to be higher than that achieved during these full mission tests. Overall, Team Animus Ferus has extensively tested Spirit 9 to ensure that the maximum points are captured during the 2017 mission demonstration. The team is very confident in Spirit 9's ability to complete all competition elements except emergent target in a single flight for the mission demonstration. Thank you for watching, and we look forward to a successful mission demonstration.